write a code and so on. But also I will introduce you to Xcos. Xcos is a way of simulation where you define your model as block diagrams. You sort of link those block diagrams that describe the model in a certain way, and then you get the results that represent the solution of the differential equations, or the model, you can say, results from doing some sort of a simulation. We'll start with logical operators. Last time we did some mathematical operation like addition, subtraction, division, multiplication. But sometimes you may need to do some logical operation. You may need to control the flow of the program by asking whether a certain condition is true or false. So to do that, you need logical operators like equal to, greater than, less than, and so on. This equal to is not an assignment operator. This one is just as if you're asking the question, is A equals 2? So if you write it this way, it means is A equals 2, it will be a question. And the answer will be either true or false. But when you say A equals 2, it means you are taking this number 2 and you are putting it in this storage device, if I can call it that way. So let's do a simple exercise here. I will go to CLab, and I hope all of you have CLab installed on your computer. So I go here and write A equals rand 3 by 3 or 2 by 2. So this will create a random matrix A of 2 rows and 2 columns. So if I press it, I will get this. Then maybe I'll ask a question, A larger than 0.6, let's say. Here I'm asking the question, is A larger than 0.6? So what it will do, it will go to each element and check whether it is larger than 0.6 or not. So this will be false, this will be true, this will be false, this will be true. So I'll get FFTT if I do it. So I'm getting FFTT as an answer. So it's not a number. What you'll get here, you'll get an answer which says whether the statement is true or false. And again, this is good when you write your program in which you would like to, let's say, make a decision whether to do something or another thing, depending on a certain condition. If A is larger than, let's say, 0.6, then do this. If it is smaller than 0.6, do this, and so on. So it's good for controlling the flow of your program. We have also a lot of math functions that you can use in CLab. This is just a very short list of the available math functions that you can use: square root, exponential, log x, log 10x, and so on. If you would like to know more about the other math function that you can use this link to learn more. So if I take that link and go here, it will give me a list of all the math function that I can use. This is from linear algebra. A lot of some of them I don't know them even. So this is just from linear algebra. From statistics, you have other sort of this is elementary functions for getting an identity matrix I, for sort of generating random numbers and so on, for the log, for the floating point, for rounding up numbers. If you want to make a number rounded up to the nearest integer or nearest sort of I mean, if you have what you call a real number and you want to convert it to the nearest integer, you can easily do it using floor or using ceil. There are other ones which are to do with trigonometric functions, statistics. So a long list of functions that you can use. I want you just to know that it is there, those functions, mean to get the average, and so on. So you don't have to know all of these. Whenever you need them, you'll be able to get them very easily. So I just want you to know that these functions are there. Whenever you need them, you can easily find them in the CLab help documents very easily. And it will tell you how to use it and so on. Now, last time we wrote most of our sort of commands in the console, in the working space here, as I just did now in the workspace here. So most of our commands, we write them usually here. You write A equals 1, B equals 2, C equals A plus B. So for simple commands, it's okay. X equals 0, and then the increment 0.1. I put it this way, 0.1 up to pi, let's say, up to pi. So when I put this percentage sign and then I put pi, this means this is a number which is known to CLab, which is 3.141. So when I do this and then write y equals sine x, I will get y, which is sine x for all the values of x that I put here. So this is okay if you're making very simple calculations. If I want to make complicated calculations or a program made up of, let's say, 100 lines or 10 lines even, it will not be okay to do it that way. Because if I make a mistake, it means I have to repeat all the lines that I have written. So to avoid doing this, you can use C notes. C notes will create or open an editor for you. And then in that editor, you can write your what you call your commands. So I can have a text editor in which I will write my commands. So I can write A equals 1, B equals 2, C equals 3 plus A times B. Whatever commands you want to write or statements, you can write them, save it, and then execute the file. So for this simple program, I don't have to do it that way. I can do it in the console. But sometimes I may have, or I may need to write a complicated code like this one. I don't want to do this line by line. It's better if I just write it in a code and then run it. So I will save this one now, save as, and we save it usually as an SCE file. You have here a number of options, but the one that we'll use for general, what you call script is SCE. So this I'll call it my first file, let's say, my first file. And then I will use the extension SCE. You cannot see it here, but it is SCE. And then I will save it. The extension here is SCE. And then I can run it either by pressing this button or icon, execute, or I can go to execute here and then run the file with echo. With echo, it means every line that I have in the program will be repeated in the console here. It will be repeated. Let me close some of these windows. We don't need them. In this console here. So if I go here and execute with echo, if I go to the console now, to the workspace, all the lines that I have in the program, A equals 1, B equals 2, will be repeated. If I want to run it without echoing all the statements, I will do execute without echo, with no echo. So if I do this, now what I will have, I'll just have this result, because I didn't put a semicolon, printed in the screen. So if I go here, I will have only, even that one will not appear. So I executed the command, but nothing have been sort of printed in the screen or shown in the screen. Let me show you again. So if I go here and run it with no echo, it means nothing will be printed on the screen, but the result will be there. C will be known. So if I run it, if I go back to here, nothing will be appearing, but C is known. So C is 5, but nothing will be printed as a result. So usually we'll do it with echo. Sorry, here. When you run it with echo. So that you can see what is happening. We can see the results of your calculations. So this is a script file, which is just this set of commands that you have written in a file instead of writing it in the working space. Instead of writing them line by line, you will write it in the in a file, and then you execute the file. And usually we save it with the extension SCE. This is for a script file. We have another kind of file that you save it with an extension SCE. This is a function file. I'll show you the difference between the two. So this one is just a script file, just like the one that we did, and you save it with the extension. You put a name, let's say something dot SCE. So this is just a simple script file, and then when you run it, you'll get this kind of results when you write it with the echo. So this is after running it, I get this results, and here is the original file, the script file that I have. Any questions regarding the script file? Okay, so I think it's easy. I'm just writing the commands in a file, and then I'm executing the file. I want one of you, so maybe Hamza Al-Hadrami, if you can write a script file. So you will share your screen. I'll stop sharing my screen. You write a script file that you define in it a vector X. I will guide you. You define a vector X, you put something in that X, and then you get the average using mean function. So this is a built-in function in C-Lab. So you write X equals something, you put some numbers here, and then you write Y equals mean of X, and so just 2 lines, and save the file with the name, any name, with the extension SCE, and then you run it to get the result. So I want you to do that. I said Hamza Al-Hadrami is with us.
Yes, I am trying to get it running.
So I'm stopping, I'll stop sharing, and then you will share your screen.
Okay, doctor, it's very slow. Maybe wait.
No problem, we can wait. No problem. You have it there with you, the C-Lab running now?
Yes, doctor. No, it's very slow. But now it will open up.
No, it will open. It will not take that much of time. So start sharing the screen meanwhile, so that we can. Okay, so you go to applications.
From file?
No, not from there. I think something happened. This is the history only. This is something happened. Yeah, there. So application, go to C notes. Now you have the editor. Now you can write here, define X. So X equals something, whatever. You have to use that bracket.
Which one?
Yeah.
Okay.
So write anything, any numbers, just put space in between.
Enough?
Okay, that should be enough, yeah. And then put semicolon so that it will not be printed when you do it with okay, and now just write Y equals mean X, which means you are getting the average of those numbers. So 2 plus 4 is 6, plus 7 is 13. So the average should be 6.5. So mean of X. You have to put it between 2 brackets.
Okay. Like this?
No, the other bracket. So that bracket is just to define vectors and matrices, but the other bracket is to give to functions, yeah. So now save it under any name.
Semicolon, we need to have it?
Yeah, it's good always to have it.
Okay.
And then go to file and just save it under any name, save as, and, yes, okay. So put it somewhere in the desktop, should be okay. So give it any name, my face file, whatever. And it's already with the extension SCE, so it's fine. So that's it.
Okay.
Save. Now you can run it by either pressing the arrow here.
This one?
Yes. So if you press it, you can see there that it is it run the file, but nothing printed. So if you go back now to the file, you have it somewhere there. Yeah. So now go to execute and execute with echo. If you do that, the results will be there, but the results of y is not printed because you put semicolon. So if you want to know what is y, just type y or remove the semicolon.
Type Y here?
Yeah. If you put y there, it will give you the result 6. Should be 6.5 or not? 2 plus 4 is 6 plus 7. No, it's okay because 13 something divided by 3 should be 4.33. Yeah. So it's fine. Shukran.
Okay.
Ahsan. So I will start sharing now my screen. So we'll continue. You can see my screen now, I think.
Yes, Doctor.
So we know now how to write a script file for a simple code. There is another type of file, which is a function file. A function file starts with the word function and end with the word end function. And then you can have some remarks. When you put this symbol, it means this is a remark. You can write anything here. And then you write your program. But this program will have an output, let's say y equals the name of the file, let's say f, and x is an input. So this kind of function file needs an input and gives you an output. And whatever you define here, let's say a equals 2, will be local, will not be known to the other programs. So you can do whatever you have here, and then at the end you have to write y equals something, so that you have the output. And you need the input. And to call it, you just write another program, or you go to the console and say, let's say b equals 3, and then you write y equals, let's say, mean of b. So this b will go here to this program as x, and then you'll calculate something, and whatever output you'll get there, you will get here in the program, the main program. This is the main program. You will get y, which is equal to this. So this is how you write a function file. Let's have an example. Let's say I want to get the average. Usually we have this function, just now we've used it. I think it was Hamza. Hamza used it to calculate the mean, the average of a number. But let's say that we don't have that function and I have to write it. So I can write it in this way. I can get x as an input and then know how many elements I have in x, let's say 5 elements. And then you sum. So sum here is a built-in function in CLab. You just add the numbers in x and you divide by how many elements that you have in x, and this will give you the average. And then you need to save it with the SCE extension now. So let me do that. So I'll go to CLab, yeah, and I will go to application, C notes, but now I'll do a function. So I'll go here and write function. As soon as I write function, I will get in function at the end. So this is the syntax of it. And then I will write, let's say, y equals get my average. Okay, and then x. So this is the input x, and the output will be y. And then I will write, let's say, m equals length of x. It means how many elements in x. Are there 10 elements, 20 elements, 19 elements, whatever. And y equals to sum of x. Sum is a built-in function in CLab. It will sum the elements in x. And divide this by m. This will give me the average. And I will save this, save as somewhere. So I'll put it somewhere, maybe in the desktop here. And now not with SCE extension. And the name of the file should be this one. This is the name of the file. So copy and then save as. And I'll put here the name of the file. This is the name of get my average, but with SCE extension. And then save it. So save it. So now the file is saved. Now I need to write another program or go to here and call it. Call this function. I need to call that function. I should define x equals, let's say, 1, 2, 2, 4, 7, just the same example that Hamza used. And then I need to write the, call the function. So y equals, I have to use the same name, get average, and then put the input x, and I should get the results. But there is a small error here. It will give me an error. It says this is undefined. Undefined because when I write y equals to this function, the program CLab will look at the functions in the current directory. In the directory that this one is in currently, which is this one. Let's see. TWD will give me the current directory. So the current directory is this, which is not the same place where this file is saved. So I need to change the current directory. So I will go to the file and I will left click or right click, sorry, and then copy full path. Right click the mouse, get copy full path. So copy, and I will go here. And what I will do, I will get directory and do this. And then, so this means I will get all the files in that directory that I will put in now. Control V. So it is this one, but without this here. So this is the directory. It seems the same one, maybe. I'm not quite sure. Let's see. So when I put this now, I am in that directory. Or at least I can get the files in that directory, that path. So now when I write this, it should work now. So when I press, I should get the result. So again, let me repeat this. You write your function. Okay, so you wrote the function. Let's say this one here that we have. So this function here that we just wrote. So you write this function, and then you go and save it under a certain name. It should be the name, should be the same name as the name of the function, and then with the extension SCE. After saving it, you need to know where this file is. So you get the path of that one, and then you write this command. So this command informs CLab that I want to use functions which are saved in this place. Now I can use it. I can use that function. Any questions?
Yes, Doctor.
Yes.
From where you get this directory?
Yeah, so let me go back to here. When you right click on the mouse, right click here, and then it will, you can copy the full path, this one. So when you copy, you will know. Also, you can see it here, but instead of writing it letter by letter, it's better to just copy the full path from there. And then you go to another program where you want to write this, or you go to the console here, and you write the command get directory, and then you put the directory name. So now CLab, when you issue a command like this one, where there is a function, it will look for this function in this place, and it will run it. So it will do it that way. Any other questions?
Yes,
So now,
Doctor.
yes, Faba.
Doctor, why we don't combine all this in one file?
That's also possible. It's possible, but sometimes you may have more than one function. So I may do it here. I may do it this way, and write, let's say, x equals 1, 2, 4, and then write y equals to this. This way, and then I run this file now. So if I run this file, it's executed, but without echoing. So if I want to echo the results, I have to execute file with echo. Now, if I go here, I'll get the results. So 2.33. So it is possible. Like, and why I'm not doing it sometimes, because you may need more than one function. You may have a program where you're using 5 functions. You can still make them all in one file, but sometimes you may have functions that you want to reuse by other programs. So you may need those files to be somewhere, and then you just call them whenever you need. Does this answer your question?
Yes, for organizing, so like.
Yeah, for
easier.
organizing, yeah. So that you don't have to worry about the mistakes if you make mistakes. So you may have a program that does several things, and then you want to make sure that whenever you are done with something, ما دام خلصت أنا هذا الجزء من العمل، إذا بخليه على جنب على أساس إنه sub program. عارف إن هذا الجزء من الحل صحيح. I don't have to go back to it. إذا حصل خطأ بعرف إنه في جزء آخر من البرنامج. So that's the reason for doing it in several files. But for our work, you don't need to do it that way, because you may forget how to do this, get D and so on. So it's better to put it in one file, for at least for the time being. For the time being, just put it all in one file, just as we did when you did the simulation in the previous lecture. When we did the simulation, let me show you that, so that you may use this in the homework. I hope I have it here. It seems I don't have it, but we had it in the previous exercise, or different in the previous lecture. It was there. Okay.
Doctor,
تفضل.
I have a question.
تفضل.
Can you go back to the previous slide? Yeah. For this problem, we save it as SCI.
As SCI, yeah.
And for the
the simple one like this, you save it as SCE. You can also save it as SCI. It should be okay, no problem. It will run it. But for some reason, they prefer to have it that way. So a file like this one, it will be SCE, and a function file like this one should be SCI.
Okay, Doctor.
Would be better, according to their recommendations. I want now maybe Maher to write a simple function file that will calculate the minimum of, I give you X equals, let's say 1, 2, 3, 4, 5, and I want you to calculate the minimum using min CLab function. So you don't have to write a very complicated code. It will be just 2 lines, but a function, and then you call it. Or just write everything in one program, a function, and just like this one. The function and the calling program, put them all in the same place, like this one. But instead of mean, now I want you to get the minimum. So I'll stop sharing, and I said Maher or not? Maher Khalfan?
But Doctor, I use my phone.
Okay, then you cannot do it. So maybe البلوشي بطي. أنا ما أدري إذا كان أنطق الاسم بطريقة صحيحة.
نعم دكتور.
تمام.
Yes, Doctor.
So if you can do it, if you can share your screen, I will stop sharing, and then you
Doctor,
share.
I am using my phone.
You are using your phone, okay.
Yes, Doctor.
Salmi? Omar?
Yes, Doctor.
Can you share your screen with us?
Yes, sure.
Okay. So I'll stop sharing. So again, go to applications. Yes. Can go to applications, and then easier to go to application, or even there, it's okay.
Sure.
Yes, C note. So you can start by putting the word function at the beginning with small f. And int function. آخر شيء. أيوة. وهناك بتكتب مثلا y equals something. Y is the output. قرب الفانكشن
اوكي.
على نفس الخط. ايوه. y equals my minimum, let's say, call it my minimum x between two brackets, the regular bracket, the regular one, not this one.
Okay.
Yes. فانت معك الحين الاكس، مجرد ما تكتب ان y equals min x. y equals min x. But it should be small y ولا كتبت انت capital y ايضا في البدايه؟
في البدايه كابيتال دكتور.
اذا خلاص بيكون capital ايضا.
اوكي.
لو تلاحظ هنا لما كتبت من تغير لونها الى اخضر او ازرق ما ادري، لانها على اساس انه يخبرك ان هذه فانكشن معرفه في سي لاب.
نعم، محفوظه في البرنامج.
محفوظه في البرنامج. ايوه. فهناك بتحط اكس. خلاص الحين بدل ما نكتب برنامج ثاني في نفس البرنامج هذا بستخدم هذا الكود. فبروح تحت الان فانكشن وبكتب مثلا x equals something او z. It doesn't have to be the same name. You can put another name. It shouldn't be a problem.
Okay.
Let's call it z. ايوه. وخلنا نخليها راندوم 110 rand 110 between two brackets, the regular bracket. بس خلينا نقول 110. فبيعمل لي راندوم فيكتور ويسمى 1, 10 which is made of 1 row and 10 columns of random numbers. وبعد ذلك يكتب y equals min
دكتور, we should appear the result or not?
We'll print the results also when you execute.
Okay.
So y equals or حتى اسم آخر ما لازم y، ممكن تسميه أي شيء، لأن المسميات هنا غير المسميات الموجودة في الفانكشن. a equals let's say my minimum z. خلاص الحين you can execute. You can go to execute with echo. So when you run it and you go to the program, you'll find the results there. فلو تلاحظ ان ال a equals this which is the minimum number اللي هو ثالث عدد في وش يسمى الزد اللي هو ذاك بالفعل. فذاك اصغر رقم موجود في الفيكتور اللي معنا. احسنت. So the program is very easy to use. It's a big program, so it may need some time to get used to it. But what I will do in the next in this lecture, in the next maybe 1 or 2, is to introduce you to the program, and then you will be using it to solve your homeworks and to do some exercises. And you'll keep on learning. It's a journey that will never end. That's true for any software, because most of these softwares are not that small. They are complex, and there are a lot to learn and a lot to do with them. And you'll keep on learning as you go on using it. So now we know the difference between script files and function files. Let's do another exercise very quickly. This is an exercise where I will write a function file to draw a circle. So I'll introduce you now to plotting. So this will draw a circle for me. So I'll be writing it. Let me go to here. I will write the function, and then we'll use it. So function draw my circle. And then the input will be the center of the circle and the radius. So there is, if you notice here, no output. There is no output, y equals, because I just want to draw the circle. So the function will just take input and plot something. So we'll now define the, let me explain it here, will be easier. So what I have the center, which is XC, YC of the circle, and then I have the radius, R. So I will define an angle theta, which changes from 0 to 2 pi, and then I will try to calculate X and Y. So if this is theta, if this angle here is theta, and this is the radius is R, what is X? And this point here is XC, YC. So in this coordinate system, XY, this point here is XC, YC. What about this point? How can I get this point and this point, which is X and Y? Anyone?
R cosine theta or R sine theta?
So X will be what? R?
R cosine theta.
R cosine theta. Let me just erase this somehow, sorry. So this one is R cosine theta. But R cosine theta is this length, this one only. But if I want to measure it from 0, what will it be?
Plus XC.
XC. So XC plus. What about Y?
YC plus R sine theta.
R sine theta. So this will give me the X and the Y, and then I can plot it. So I will go back to my program here. So I need to calculate X equals to XC plus R times cosine theta. And the same for Y. Y equals YC plus R times sine theta. But I didn't define theta. So I need to define theta. So I'll go here, and I had to define theta. So theta equals 0.12 times pi. So this will define theta for me. But also, I need now to calculate it. I can do it this way. This will give me also an answer. No problem. Let's try it this way first, and then we'll do it in a different way. So now I have X and Y. And now I want to call this function. So one way of doing it, I can save this and then go and call it from a different place. But let's just do it in one program. So let me save it first with this name. Copy, save as. Draw my circle, SCE. So now it's saved. I can go here and define my center. So let's call this X1 equals, let's say 4, Y1 equals 4, and radius R, capital R, equals 2. So these names don't have to be the same as these names because these are local. These are defined here only. But when I call this the function, it will know that the first number is XC, the second number is YC, the third number is R. So I can go here and call the function. But will it plot now? Is this plotting? Will it plot?
No.
It will not plot. So I need to call it to tell it to plot. So plot X, Y. Now it will plot it. So now I can save it, save, and run with the echo. So run the file with echo. And if there is no mistake, there is undefined variable XC. So there is a mistake. So I have to go back here. XC is, here it's not defined. So I need to change this to X1, Y1, and R capital. Now I can run it. So execute with echo. So I got the circle drawn. So this is my circle with the radius, with the center at 4 and 4, and the radius is 2. So I can,
Why theta you put 0.1 there?
0. This one you mean?
Yes.
Yeah. This means my theta will start from 0 with an increment of 0.1. الزيادة بيكون كل مرة 0.1 لين توصل ل 2 باي، فبغطي الدائرة كاملة. فببدأ ب0 theta with an increment of 0.1, so 0, 0.1, 0.2, 0.3, 0.4, up to 2 pi.
I got it.
So this will create a vector for me. And then when I do it this way, this will sort of calculate x for all theta. This is one way of doing it, but if you want to write it as in this way, so n equals length of theta, it gives me all the, how many elements is in this vector, 10, 20, 100, 200, 1000. And then I can write a for loop for I equals 1 to n, and I will take this one here, cut it, and put it here in this for loop, and calculate my xi and yi element by element. Instead of using the whole vector, I will do it element by element. So this is at theta I, and this is at theta I. I should get the same results. But here I'm using the for loop to calculate it one by one in case you need to do it that way instead of taking the whole vector theta and putting it. Sometimes you may need to do it this way if you want to do something different in different elements here, instead of taking the whole vector theta as we did before. So if I run this one, it should give me the same results, unless there is a mistake. So I'll check it. Yeah, so it's fine. So that's why I got this. If I want to make sure that it's a different one, I can change the this one. Let's say the circle is at 0, 0, and the radius is 5, and run it. It draws it in the same place because I didn't close the previous figure. So this is the first circle, and this is the second one, the second circle that I have. Any questions? Okay, so this is a function, and I'm executing the function. So instead of writing it in the same file, I can also do as we did before. I can call it in the console or write another function and call it instead of putting everything in the same file. So for plotting, you can do other things besides just giving the plot. You can put also the title. You can put an x-axis. You can label the x-axis. So this is the title, and then this is the x-axis, and this is here the y-axis. So you can plot, and then you can use the word x title to give it a title, x-axis, and y-axis name. You can label the figure. And also you don't have to use you can say the same line for different plots. You can change how you draw, and the color and the font and the width of the line. You can control that. So here I'm drawing sine t and y and cosine t and tan t using different lines. So this one, sine t, it is red with O at every point. So O, and so on. The cosine is green with the plus and a minus sign. So green with plus and minus sign as the marker. And the tan, it is blue with the line which is dotted this way. And there are different options there that if you want to learn more about it, you can just write again help here, CLC, to clear the screen. So clear the screen, and then write help plot. It will give you the different, you can say, options for plotting, and what you can do, and even examples. So you can learn a lot about plot, we don't have to go through it now. You can even have 3D plots surface done very easily. So if you want to learn more about it, you can just write help a plot, and it will give you all the information needed about plot. So we don't have to do that exercise today. You will learn it as you use it very easily. So again, if you want to get any help regarding any command in CLab, just write help and the name of the command. You can also do subplot. So I can plot, this will appear in one window. So this is 311, meaning I will have 3 rows, 1 column, and the first plot will be this. And the same here, 312, it means I'll have 3 rows, 1 column, and the second plot is this. Let me do this. This is a good sort of thing to do sometimes. So let's say I define theta to be 0.12 times pi. And then y sine is equal to sine theta. And y cosine equals to cosine theta. And y tan equals to, or let's just do 2, okay? And then I'll use subplot. So subplot 2, 1, 2, 1, 1. It means I will have 2 figures, which are, 2 rows of figures, 2 rows and 1 column in this way. And then the first one will be the one that I'll plot now. So I'll write here plot t y sine, okay, and then subplot 2, 1, 2, the second plot now. Here I'm having 2 plots. 2 times 1 is 2 plots, 2 rows, 1 column. So the first one is this, and the second one will be this one, plot t y cosine. So if I run this, I'll get this plot. Oh, sorry. There's something wrong. It could be that I have...
Doctor, you wrote 8 instead of multiplying in first line.
That's why then. Okay. So this would be 2 times, yeah. So now I can execute with echo. And I'll go to the figure, but this one. But somehow the circles are still there. So let me close it. When you... Either we close it here, CLC, CLF. CLF will clear the figure. So now I close the figure. Okay, so there's nothing in the figure now. And then I will go and run it. Execute with echo. So now I have the 2 figures, 2 rows, 1 column. I can have it in different ways. If you write it as 2, 2, it means you'll have 2 rows, 2 columns, and I'll have only 2 figures written, or plotted. So when I do this now, I will have, again, because I'm plotting on the same figure. So let me, again, what I will do, I'll do it here maybe this time. CLC, and then CLF. So it will close the figure each time I run the program. So now we have 4 figures, which will appear in the same window, but I've defined only the first one and the second one. The third and the fourth are not plotted, but the space is there for them if I want to plot extra figures. So this is subplot. Again, if you want to know more about subplot, just write help subplot, and you'll get some more information about the subplot. So there are a lot of capabilities for graphing and for plotting your results in CLab. You'll learn them as you use these facilities. So we don't have to learn everything today about plotting. So the second part of the lecture now is how to use block diagram, something like this, the one that we have here in front of you, to do some simulation. So here I'm defining my model as a transfer function, we call it. and you have the input, in this case is a step input, and then you are getting the output in the screen. So this is just a screen. So we'll learn how to do this. But before that, we've learned last time that if you have equation that represent a model of the system, you can write this equation as a set of first order differential equation using state space. Or if you take Laplace transform, you can write it as a transfer function. So very quickly today, I will introduce what I mean by a transfer function, and then we'll use it for simulation. So let's start with the Laplace transform. I think you've taken this in differential equation. The Laplace transform, you transform an equation, usual differential equation, from the time domain to the S domain. In the S domain, you'll have algebraic equations. And here you may have some derivatives and so on. But once you are in the S domain, you'll have only algebraic equations. And S is a complex variable. So if I want, let's say, to get the Laplace transform of this function in time. So this is a function in time. Ut is just a way of saying that this one is 0 before t equal to 0. And then here it is defined as such. So it will be e to the minus at. So ut is just this function, a step function. And then when I multiply it with any function, it means that function will not be defined what you call for values of t less than 0. So if I have, let's say, x or f equals x squared. So if I have this x squared, it means it is this one. And then when I multiply f, which is this x squared, when I multiply it by u, which is this one, it means my function f now will be this. This will only be defined for t larger than 0. It will not be defined here because I'm multiplying it by this function, which is 0 before 0. So it's just a way of defining the function such that it is not defined for t less than 0. Now, if I want to get the Laplace transform of this, I'll just substitute into the definition for the Laplace transform. So this f of t will come here, which is this one. And then if I substitute, what I will get is I tried just to get rid of whatever I wrote, but it seems the PowerPoint. Yes, so it's okay. So I'll go back again. So if I substitute with f of t equals to this here and use the definition of the Laplace transform, I will get f of s to be this one. Now I have to sort of substitute with the limits of my integration. You understand this step here all the way to here or not? Is it okay?
No, doctor, please
Explain it. Okay. So, okay. So instead of f of t, I put this. So I put it here as a e to the minus at. Now I'll take a as a common factor. You can just remove it and put it outside. You can remove it from here and put it there. Okay. Now minus at and minus st, I can add them up because I have e to this power and I have here e to this power. Just like when you have 10 squared times 10 cubed, you can write this as 10 to the power 5. You can add 2 and 3. So I did the same here. I added these two and I took the minus sign outside. So s plus a times t, d of s. Now the integral of this is what? You take this constant and you put it in the denominator. A is already outside the integration. And then the integral of this one is simply the same exponent, or not? What is the derivative of d, let's say, by dt of e to the minus alpha t? What is the derivative of this one? Anyone?
minus alpha e to the power minus alpha t.
Yes. And what is the integration of this one? If I want to integrate this, what will I do? I'll take minus alpha outside, and then I have e to the minus alpha t. What is the integral of this one?
1 over minus alpha.
Divided by t.
Yeah, so I have to divide it. So over minus alpha, e to the minus alpha t. So this will go with this, and I will get this one, the same one. So I need to divide by this. So this is what I did here. I took this one, I divided by that, and then e to the minus bracket s plus at. Now I have to substitute with the limits of integration. So when I put t equals infinity, what will I get? With this minus here. E to the minus 100 will be what? 0.
0.
So 0 minus, and then I have already a minus here. A over s plus a. And when I put t equals 0, what will happen? E to the power 0 will be 1. So, and this minus is there. So this will be a over s plus a. So this will be my Laplace transform. So this function in the t domain, it will be represented by this function in the s domain. So Laplace transform is just a way of transforming your equation from one domain to another, from one representation to another. Why we're doing this? Because for solving differential equations, when you do the Laplace transform, you transform derivatives and differential equations into algebraic equations. بيكون مجرد عبارة عن polynomials and ratios of polynomials. So it's easy to deal with it. And then you solve your differential equation by rewriting your S functions in a certain way to use the tables to go back to the time domain. هذه بنشوفها في المحاضرة القادمة. فالمهم ان اذا سويت كذا انا ممكن اغير المعادلات من معادلات تفاضليه الى معادلات في الاس دومين which are معادلات جبريه. So the sort of the Laplace transform of this one will be this, as we did just now. The Laplace transform of sine will be omega over s squared plus omega squared. The Laplace transform of cosine will be this. And you can have a table of all of these functions. And also for the derivative. So the Laplace transform of a derivative f dot is s f of s. And initial conditions. The Laplace transform of f double dot will be s squared f of s and some initial conditions, and so on. And we have some other properties that you can make use of. So I can take a differential equation. Let's say this differential equation, mx double dot plus k dx dot plus ks equals to x equals to f. Let's say this equation. This one will be in the s domain. It will be m, which is a constant, s squared, sorry about that, m s squared x, so with some initial condition. Let's assume that the initial condition is 0, plus kd, and x dot is s, x of s, plus this one, the Laplace transform of this will be simply x equals to f. Okay. Now I'll take x as a common factor. So I'll take x as a common factor. I'll have ms squared from here plus kds plus k equals to f. Then I'll define something called g of s, which we call the transfer function, which is the ratio of x over f. What will that be from this equation? What will be in the numerator? When I get x over f, x equals to this. So f equals to x multiplied by something. So this will be 1 here in the numerator. What about the denominator?
Like f squared, maybe.
Yes, ms squared plus kds plus k. Because 1 times f, which is this, equals to x times this, which is that. So this one equals to this. So this ratio x over f, we call it the transfer function. And therefore I can write it also in this way. I have the input f, I have g of s, the output will be x. So f times this will give me x. So f times g of s will give me x. So I can write it as f g of s equals to x. This we call it the transfer function that relates the output to the input. And now I can use this block diagram in X course in the C lab. I can take this, call it, what you call representation of the model instead of this equation, and use it to do simulation. So that's what we will do. So let's do this simple exercise. Well, let's find the transfer function of this one, and we'll ask here maybe Rashid Al-yahmedi to help me out. What will be the Laplace transform of this? The derivative of C, dc by dt. What will it be in the Laplace transform? Maher, Majid, anyone?
1 over t square.
Will it be that way, or let me remind you of the table? This table, f dot is f of s with initial condition. So if we assume its initial condition to be 0, f dot is f of s in the s domain, and f double dot is s squared f of s, and f is simply capital F in the s domain. So to move from here to the s domain, you just write it as f. If you have f dot, you write it as s f of s, f double dot s squared f of s in the s domain. So if you go back to this equation, this is the first derivative. So it will be what in the s domain?
S50.
sc of s plus this
2f,
one, it will be just
2c,
tc equals to r of s. So now if I want c over r, what will it be as a ratio? This I can write it as c common factor. Here we'll have s plus 2 equals r, if I take c as a common factor. So what will be my transfer function in this case? C
1 over s plus 2.
S plus 2. So this will be my transfer function. So this is what we have here. Let me erase it. So this is what we have. This will be my transfer function that relates C to R. I think there should be a equal sign here between G of S and this ratio. Let's skip this part. So X course allows you to use transfer function to do the simulation. And to start it, you go to applications. Instead of C note, now we'll go to X course. And when you open it, you'll have two windows. One window where you'll put your model, and another window where you have the blocks that you'll use for simulation. And for this simple exercise, we'll need an input. Let's call it a step input. If we go back to the to this here, to this example. This one here, the input f is, let's say, a step input, a constant, and then I want to find x. So this input f is the step input. I have to define what is the transfer function, and then I will get the output x. I can plot it. So if I do that, I need this simple blocks only. I need the input f as a step function, and then I need to define my transfer function, and then the output, to visualize the output, to see the output. This is just a clock. I will need it in some blocks to define time. So let's do it just in the program, there will be better. So I'll go to the program. Yeah. Okay, CLC again to clear the screen. And then you go to application and you go to Xcos. So I'll have two windows, this one and this one here. And here you have lots of functions or blocks that you can use. But for today, we'll use sources to define the input, sinks to define where the output will go, and continuous time systems to define our transfer function. So let's start with sources. We'll take here a step input. Okay, you just what you call copy or drag and place your blocks, and then we need a sink, a place where to put our results. We'll use for today only this one, cscope, and you'll notice here we have this red sort of arrow, which means this needs time as an input. And then we'll go, so the sources, from the sources we got the input, from the sinks we got the screen where the results will be plotted, and then continuous time systems will get our transfer function. It will be continuous, this one, continuous continuous time function, sort of. So we'll take this one, CLR. You can also define it using this one, the what you call state space description of the model. But for today, we'll just use this one here. So you put it, and then you connect the elements or the blocks. So I'll connect this to this one, and I'll connect this from here to here. But I need time also for this, so I'll go to sources and take a clock and connect this one to this. Okay, and then I can just rearrange things a bit just to make it look nicer. And then you define your function, this one. So if you double click, you will define your numerator and denominator. So if we want to change the denominator, let's say to s squared plus 1.4 times s plus 1. Let's say this is my transfer function, numerator over denominator. And I'll go here, double click. This is the step function. So step time is 1, I'll make it 0. I mean, the change is start at 0, and then the maximum value is 1, and the initial value is 0. Because here I'm defining a step input. I'm defining something like this, a step. So I'm telling it that the final value, this one is 1. The initial value, this one is 0. And the step point, this one here, instead of starting from 1, I'm telling it start from here. So the function will be this way. So it will change from 0 to 1 at 0. So this is basically what I'm doing in that definition here. When I go back here, double click. So 0 is step time, 0 initial value, final value is 1. Okay, so I have all the elements. I think I have the connection here not done correctly. So I'll go back and connect this. Now I'm fine. Okay, and I will execute the do the simulation, simulation and start. So simulation and start, or you can do it from here by pressing this icon, and the results will be appearing in this screen. So when I press it, simulation in progress. Now the results is there. So I have the results, but it's not that clear, the figure. So I need to zoom in to see the results. So I can go here, you have different options. This one says reframe. If you can notice, I don't know whether you can see it, reframe to content. When I press it, it will somehow zoom in into the figure that I have. So I got this as my results. So any questions? We did a simple exercise today. Any questions?
Doctor, can you repeat from where we get this icons?
Okay, so let me start from the beginning. So I'll close everything. It asked me to save it, but I will not save. Okay, so we'll go back to the C lab. So here, I will go to applications, X course. When I open it, I will get these two windows. Here where I define my model, this one, here I will define my model. And here I have the blocks. And for today, we'll do a very simple one. We'll just use sources to define the input. So step function, let's say, as my input, and sinks to define where I will get the results put. So in this case, I will use cscope just to put it in a screen where I will show the results. And then you define your, so you need sources and sinks and continuous time. So here we'll get this, this transfer function. I just need to define it. And then you double click and you define your numerator and denominator. So here I've said that I'll have it as s squared plus 1.4 times s plus 2, let's say. I can make it a bit wider so that I can see. Okay. And then I connect them. So I connect this arrow and this one. But now you'll notice that I have this red head of an arrow, which means this one needs time. It needs time as an input. So I'll go to sources and I'll get the clock. And I'll connect these two. So I'll connect these two arrows, these 2 points. Oh, sorry. Okay, so I have this connected now. Is that clear, I think?
Yes, Doctor.
Now I just have to, if I want to make few changes in this one, I'll double click, let's say on this one. Instead of step time being 1, I can make it 0. And final value, instead of 1, I can make it 10, let's say. But I'll just use the default values. I will not change it. This way, when you double click, you can define your function. And then you can also change things here and there. But we don't have to do that unless you know what you are doing. But for the time being, there is no need to change anything here. This is just a screen, but you can change few things in it. But there's no need to do that. You can change what is your Y minimum, what is your Y maximum, but you can do that after plotting also. So you don't need to do it at this stage. And then you go and do simulation. So you go to start and you start your simulation. So you got the results here in this window, which is this screen. So this window here is this actually. So we want to, let's say, zoom in to see the figure in a better way. So you'll go and do this, press that one. It will reframe, it will zoom into the reframe to the content that you have. So you'll get this results. You can control the figure in a better way by not sending it to a screen, but by sending it to the console, to the workspace. And then you plot yourself using the plotting, command. So to do that, I will go to sinks. We still have some time. And instead of sending it to the screen, I'll send it to the workspace. I will send it to the workspace. Okay. I will keep the screen. So, but I'll just close it. So I'll take this one. I'll take the output from here. Okay. Okay. And when you do this, right click and then link style and make it optimal, it will draw it in a better way. And then you can notice here also I have this head of the arrow, which is red, which means I need time also as an input. So I'll take it this way and put it here on this line, connect it to this line. Again, I will right click, line style, optimal, so that it will do it in an optimal way. So now I have the results will be sent to here. I will send the time and I will send the result to this workspace, and the variable name is A. I can change the variable name. Instead of A, I can call it my Y, let's say. My Y. Okay. So the variable name now is my Y. Now, if I run this simulation, the results will be plotted in this screen, but at the same time, it will be sent to the workspace. I can get access to it as numbers. So I will simulate, start. Okay, so I have it here. This one is this screen. And again, if I do this, I will get this as my output. And you notice here, it starts from 1 because I didn't change the step function. The step function starts from 1, not from 0. So here it's still 0, and then here at 1, it jumps. Now I can plot this myself later. I can go to the workspace. Now go to the C lab here, the console. I have A, so not A. I called it, I think, my Y. I think it is my Y. Yeah. So I have the values and I have time. And I can plot those values against time. So I can say plot, and then my Y time. Dot time means I'll get access to this part of the output, which is time. If you notice here, you have time and you have the values, the output. So you have both there in this variable in the workspace my Y. I mean in the workspace, but in the variable my Y. So my Y dot time, I will get access to the time part of it, and my Y dot values, this will give me the values, the output, and then I can plot it. So if I do that, I'll get this as my output. But if you'll notice that it is drawn in the same place, so I need to close that window. That's the previous plot where we plotted the circles. Now if I do that, I'll get this as my output. For some reason, it started from 17 instead of starting from 0. So I'm not quite sure why is that. I think it saved the file. I mean, it saved the output here because I did have the previous figure also drawn. Let me just figure out how to get rid of this. I'll go to this one and change the buffer, size buffer. I'll put it as 500. And then I will clear the this one and close the window, CLF. So I'll go and run it again. Okay, here it is okay. It is from 0, starting from 0. And then if I do this, this is the figure that I get. So now I'll go and plot. Now it started from 0. So this is the second figure that I plotting using plot, this one. Any questions?
It's clear, Doctor.
I think I gave you too much today, but I think once you go again to the video and try yourself to do all of these things by yourself with the software, you will learn all of this, what you call concepts that I've introduced today. Even though there's a lot to digest, but I'm sure you'll learn it easily. So try to do the homework. The simulation will not be done by using Xcos, but you will use ODE. We did this last time, ODE. If you want to learn more about ODE, just write help ODE to do the homework, the first part of the homework. So here it will show you how to do it. And here's an example. Let me copy this, go to here so that you can see it in a better way. And I will open a new file. Okay, so here you will define your output, but you will have two equations. Y dot 1 equals Y dot 2 equals, and then Y naught will not be only 1, it will be 2, so 0 and 0, let's say. And then you do your, you call the function and you plot it. So I'll put this in the, what you call in the presentation that I will upload so that you can see it for the homework. So I'll do here an extra slide. You have it here.